using right now. The first one is the symmetric cryptography. The other one is the asymmetric or public key cryptography. Symmetric cryptography requires the secure delivery of the key to two parties. And it was more commonly used in the Cold War era. And nowadays, you are mostly use or receive the keys for cryptographic tasks via public key cryptography, or let's say asymmetric cryptography. So it simply works the following way. You have the same key on both sides. You just have the plain text. You encrypt it using the key with the known algorithms. In all cryptographic schemes, the algorithms are known. So the unknown part is the key. Okay, then you encrypt the message and then you send it. The same key is used to decrypt the message. So that's how you do the communication in the symmetric cryptography. And the security of symmetric algorithm relies on the secrecy and the randomness of the key. Secrecy means you need to somehow deliver the key to two parties. In the Cold War era, people were using spies, agents, but nowadays we are using some computational tasks. And I would like to mention one thing that, symmetric cryptography schemes are considered secure against the quantum computer assisted attacks. So even if you attack with a quantum computer, you can use the symmetric protocols safely. But then how do you deliver the key? That's the problem. Okay, the other set of protocols is the asymmetric cryptographic protocols. The one usually uses the prime factorization problems or discrete logarithm, which can be reduced to period finding problems similar to prime factorization. These are pretty good. So these protocols are developed after the powerful computers are developed. But now there's even a more powerful computer coming up, which is quantum computer. So it can use the Shor's algorithm and effectively apply the quantum Fourier transform to find the prime factors of large numbers. Therefore, the RSA elliptic curve cryptography is kind of commonly used. Asymmetric protocols are not safe anymore. So then the problem is, how can we deliver the keys to legitimate users? So then the question is, can we find some algorithms that do not rely on the prime factorization so that the quantum computers cannot be used for finding the prime numbers? So, which is the field of post-quantum cryptography. And as in a symmetric protocol, you have two keys for encrypting and decrypting, and there's a repository. You have to trust the repository. We do trust the repository. So for authentication, digital signature, all types of protocols that we are using nowadays, we are trusting the repository. In this case, the repository means the host, basically. So you have to trust. And the security is relied on the mathematical difficulty of the one-way mathematical difficulty of the problems. Okay. So, and let's continue. So now the quantum computer is a possible threat. What are the solutions? There are two possible solutions. The first one is the quantum key distribution. The solution comes from the quantum mechanics itself again. We can use the photons to solve the secure key delivery problem. Another alternative is the post-quantum cryptography. That's a general name, actually. I don't know why people gave that name, but post-quantum cryptography has nothing to do with the quantum. It is still some mathematical algorithms that are used for cryptographic tasks. But in this case, you do not use prime factorization or discrete logarithm so that quantum computers cannot practically or efficiently attack. So basically, we can have an entangled photon source in the center, as you see over here, and then you have Alice and Bob. They are both having their polarization analysis or whatever type of entanglement they are using. They do that degree of freedom, and then they have their analysis, and then eventually they have a key. Of course, they need to have a classical channel so that they communicate. That's why there's nothing going on faster than the speed of light. That's a myth. And with this classical communication, they can find their keys, and they can use this key for any type of symmetric protocol like AES, Advanced Encryption Standard, to communicate securely. So there's one solution, and the local randomness and the distant correlations can be used for entangled-based protocols. There are also prepare and measure based protocols. I'll be also having some comparison for these protocols as well. The second one is coming from the again the mathematical studies, post-quantum cryptography. I put the NIST cover here. Soon I will come to the point why I put their name here. But there are two possible approaches, and we need to understand basically what are the pros and cons of each approach, and what should be the way to go. Okay, so one possible question, if there are any cryptography people among us, this is the possible question that I might get. I usually get this question a lot. Quantum computers, global quantum computers, there is still time for that. We are taking too much precautions and spending too much money on a problem, a threat that does not exist yet. Well, that is not true. We don't know if someone actually had a global quantum computer. It's possible that that might be some confidential information and they keep it secret for 5-10 years and do some tasks. It's possible. We don't know that. So most of the quantum studies have some confidential sections. So maybe this is something that, that is not publicly announced. But what we know is, it's not publicly announced that there is a global quantum computer. Let's assume that that's the fact and that's the truth. In that case, should we still take some precautions? The answer is yes. I put some, I thought you might be reading the text because there are lots of examples. I just wanted to find some recent examples of some strategic information leakage or cryptographic attacks, and how can they attack each country's destiny or future. So there are lots of attacks ongoing here. Unfortunately, the resolution is not clear, but I can tell you one thing here. So here is Turkey. There are 6 attacks in 2020, from 2016 to 2020. And Pakistan is here. There are 9 attacks. So we are all covered. We all are victims of this kind of attacks. And these attacks are not done by some random hackers. These are conscious efforts of different countries. And some of them are already given here. You can have a look at them. So therefore, the cryptographic security is always a national security concern. So you cannot just say, well, quantum computers, there's the time for that. Let's just focus on now. No, you have to take precautions. Because if there is any problem with your cryptographic or cybersecurity precautions, you cannot just change the whole country's infrastructure within a year. It will take a long time, lots of money. So the logical way to continue is start taking precautions in parallel to whatever you have already. Whatever critical infrastructure we have for cybersecurity, we should start taking some precautions in parallel. So therefore, I think the question is answered. So the cybersecurity is too expensive if you don't pay right now. So we need to start taking precautions. Okay, so I'd like to talk about the US view on QKD and PQC. And the reason why I mentioned NIST, National Institute of Standards and Technologies, for PQC, because they had this surprising announcement a couple of years back. And you can read on this site that, the quantum key distribution is only a partial solution. These statements are from this report. You can find it on this link. Quantum key distribution requires special purpose equipments. Quantum key distribution increases infrastructure costs and insider threat risks. So basically, the threat might be insider as well, right? So then the quantum key distribution makes us more vulnerable against this kind of threats. And then securing and validating quantum key distribution is a significant challenge. And finally, quantum key distribution increases the risk of denial of service. Due to all these things, the concluding statement, US will not ever trust on QKD. It's not going to be allowed to use any official data transfer. That's a big statement, by the way. So because of the big, bold statement here, the rest of the world have actually had a look at it, and then especially Europe, because doing lots of businesses with US. So therefore, the infrastructure should be compatible, right? Because there are lots of ties, United Nations and NATO, all these things. Certain things should be compatible. Because of that, they also changed their strategies. And I would like to mention that this bold statement is not, well, this is my subjective opinion, not justified by this statement. Let me just briefly mention why I do not totally believe on these things. Only a partial solution, correct, but that's what we need. We just need the key distribution problem. Otherwise, symmetric protocols are safe. So we don't need to complete cryptographic tasks. We already have the cryptography. AES is already being used, right? Used in some mobile applications, right? So we can continue using them because they are safe against the quantum computer-resisted attacks. But then the problem is key distribution problem. So yes, it is a partial solution, but that's all we need. So that statement is not a justification. The second one, quantum key distribution requires special purpose equipments. That's correct. Yeah, well, we don't use them. So, and that statement is correct. Increases the cost of the infrastructure. I will be giving some examples of this one. The cost is a relative term. It's all about the serial production. If you have a serial production line, things can get cheaper, 2 orders of magnitude. There are examples of this. I will be talking about them in a while. So that is not a justification either. And then validating quantum key distribution is a significant challenge. Well, that is correct, but you know, sometimes you need to go into the challenges if there's a good solution. And risk of denial of service, that's also true, but at the same time, the other any type of cryptographic protocols are vulnerable against the denial of service attacks. What if someone puts a RF jammer? You stop communicating. So I don't think that's a justification either. So that's why these justifications from this report does not explain this statement. I will talk about some academic rumors and gossips. In the conferences, when people usually chat, you know, and this is the Quantum Industry Consortium, QUIC. It's mostly European, I would say. And if you look at the patent numbers, it tells a lot. Because usually, if the new technology is coming up, wherever the most of the patents, especially industrial patents, are located, usually the market becomes largest there, right? There's one-to-one correlation. So we can anticipate that as well, but the reports also support that. And if you look at this is China, this is US, this is Europe. And the red one is quantum computing, yellow one is quantum communication. So China has 3,000 plus patents, and US has 500 plus. So that's 7 times. And if you look at the quantum computing, it's the inverse case. And if you look at the news, I think you will understand that, you know, the actual justification might be lying down there. See, Alibaba Research shut down quantum computing lab amid restructuring, and they just gave their quantum computer to a university for studies. And they said that they will not continue anymore. Might be because of the patents and losing the edge to US. Similarly, US might be having the similar approach on the quantum communication side, but I think the gap is larger for quantum communication case. So that might be one of the reasons. The other reason is NSA is trying to hack all these protocols, and they do not want to work with something that they cannot control. That might be another approach. There's other type of the rumors, but this is one approach. So the patent track might be the actual reasoning. Regardless of that, once the word is said, so then the world is taking a reaction to that, and Europe was affected by that. And I can say like most of the Horizon Europe fundings, they explicitly start saying that we're not funding any of quantum key distribution projects, regardless of how novel it is. The topic, quantum key distribution, will not be funded anymore. They explicitly say these things in the proposals, calls for proposals. And but there's already some infrastructure and lots of money has been spent. So what's Europe gonna do? Because Europe is kind of in the middle, right? So what's Europe is going to do? Let's try to understand what they did and why they did it. So basically, they have some infrastructures, especially on the satellite part. They have this Eagle 1 studies from European Space Agency, and they split into 2, Saga and Eagle 1 approaches. In Saga, that is the first market for QKD, classified fields, only QKD. So this is basically more critical infrastructures, more critical data transfer. So they would like to focus on QKD because it's more secure, and they would like to focus on that one. But of course, there'll be some other industrial use cases as well. They would like to include those things as well. But honestly, I don't know many companies who knows what's going on in the Saga part. But on the Eagle One part, it's more straightforward. It's a hybrid approach, public QKD plus PQC, planting optical ground stations so that you can receive the keys from satellites. So that's basically something that anyone can anticipate. So basically, they are positioning themselves in a way that they are also ready for PQC to be kind of compatible with the rest of the world. And all these players throughout the continent and the projects and flagship programs, they are all kind of positioned accordingly. So who's right, who's wrong? So let's talk about the security of the quantum key distribution. There are lots of, well, cryptographically, we're calling it unconditional security, and the security relies on the quantum physics rather than some device or some people. But at the same time, there are side channel attacks. And if you look at, these are some of the papers that I put together, some of the approaches, let's say, for attacking the quantum key distribution systems, side channel attacks. The lower two are our papers, our group's papers, actually. The others are from the literature. And if you look at this, you realize that 3/4 of those papers, those studies are focusing on the detectors. Detectors are like the weakest point of QKD, where the quantum information is turning into classical. So detectors are leaking lots of information. One should be really careful about the detectors if you're building a quantum key distribution-based network. And the solution requires measurement device independent QKD, or more general term, if you also want to focus on the Charlie entanglement source, you need to also focus on this device independent, a little bit more challenging. And by doing that, you can also focus on, cover 16% more of this type of attacks, because 16% of the attacks also focuses on the vulnerabilities of the Charlie, the entanglement, the center, basically. And the device-independent quantum key distribution requires loophole-free bell test, and I think it was the major loopholes. All three of them were covered together simultaneously in a paper in 2015. I think it was a study in Delft, but maybe somewhere else. I'm not sure. But I think this is a really, really high-quality work, and it's not easy to make devices commercially available in that perspective. So, although it is proof of concept is possible to make devices that are device independent, it's not that easy. So therefore, these attacks should be studied, and there are countermeasures here. The resolution is, I think, it's my bad that I put it small, but, there are countermeasures here, and these are the attack mechanisms. These countermeasures should be studied, and there should be more and more attacks so that the engineering standards become solid, and then QKD can be a reliable protocol. Okay. Let's look at the standards of the QKD. So what do we have so far? There are 4 set of standards here. The most relevant one is the ETSI standards. But if you look at them, you will see that, if you read the whole documentations, you will see that, it's like the vocabulary, architectures, and it's just defining what is QKD. It doesn't tell much. And future priorities should be about the interoperability. What's the meaning of that? So, for example, in a recent meeting, NATO was talking about this interoperability, and they have the Cisco devices where they use skip protocol, and they were saying that, well, we cannot just change the whole infrastructure, communication infrastructure, just because of QKD. If you would like to do some QKD experiments, make sure you can integrate it to existing infrastructure. So that is another concern actually the most important concern for the engineering standards. It should be compatible, otherwise people are not going to abandon what they already have. They will not put it in the trash just because we are having a new technology. So that's why good engineering standards are needed. And in that sense, the side channel attacks should be studied more and more, because there are lots of side channel attacks. We are not aware of those things yet. And I think that part is going slower than building the quantum networks. People spend so much money and effort on building quantum networks, then studying the vulnerabilities of such systems becomes secondary, which is not healthy in that case, because the engineering standards cannot be built if that's the approach. That more cryptanalysis studies needed for quantum key distribution. Let's talk about the cost of QKD. In that NIST report, they were dedicating certain amount of percentage of the document only talking about the cost. Yes, it is expensive. I mean, you can see some numbers here. It is expensive at this stage, but at the same time, it can be made much cheaper. And I would like to give some example here. For example, an avalanche photodiode, which is a simple diode, is costs $400 to $3,800. The cheapest one is $400. Well, we are building detectors. I know the price range very well, and there are only a couple of 2 or 3 companies who are selling the avalanche photodiodes, and the prices are like this. And they are not even having a proper serial production line. They are startups. They cannot. If you ask, for example, 100 detectors, they say, okay, I can only deliver it in 8 months, something like that. So we are working with the startup companies. If there are some factories making this kind of APDs, the price is going to drop significantly. And the example, I just put this example. You can also find this. These CMOS camera sensors. I'm talking about the megapixel cameras. They were developed in NASA, millions of dollars of project cost, just to develop a megapixel camera. And I'm sure anyone in this room has some form of these camera chips, which are costing less than $1 right now. So we are coming from millions of dollars to less than $1. So that's 6 orders of magnitude. And how long did it take? We're talking about 90s here, and I think late 2010s, like 20 years, 6 orders of magnitude. So cost is not an actual concern. So if someone is talking about a cost of something, most probably there are some other issues in this case, because there's only a problem of serial production. If you build a factory, you produce thousands of them in a day, then the cost drops a lot. So that's why the QKD cost can be dropped significantly. And if you look at all these setups, for example, for BBM92 protocol, you need at least 8 detectors. And if the price of one APD is $3,000, forget about the detector itself. I'm not talking about the module, just the diode. Okay, 8 times 3,000 or 4,000, but $30,000 only goes to APD. That doesn't mean that that's the actual cost. It means there's a need for serial production. So the cost can be dropped significantly, orders of magnitude within a couple of years. So in that case, you need to understand like what is the meaning, what is the meaning of dropping QKD? Does it mean like dropping the quantum networks, or does it cause any other things for us? So that should be considered carefully. So there are lots of quantum networks all around the world. If they are built in entanglement case, they can be used many other purposes, not only for cryptographic communication. So you can see on this table that the secure communication is only these top 2 lines, and the rest is some other things that you cannot classically do with any other task. You need to use entanglement. So you can use it for distributed quantum computing, like the one in the Quantum Internet Alliance. You can also use it for sensing and metrology. You can use it for quantum GPS, quantum positioning, navigation, and timing system, or PNT systems. And also you can do lots of fundamental physics. There are many other things that we don't know what we can do with the entanglement. We just learned about entanglement. We just learned how to play around with the entanglement. We don't know many things. I'm sure if people continue studying, there will be other things coming as well. Therefore, building a quantum network is not the same thing as quantum key distribution network. These 2 things are totally separate. So summary, while QKD is this foundational application, an entanglement network's true potential lies far beyond quantum key distribution. And this is a good example. US had stated explicitly that we will not continue with QKD, but at the same time, they keep accelerating on building quantum networks. So once you build the network, you don't want to use it for QKD, that's perfectly fine. There are many other things. There are n-1 other things that you can do with the entangled networks. And there are examples of this, and they published this report in 2024. And in that report, like there are lots of things, but I will just summarize it here. 5 Department of Energy, National Quantum Information Science Research Centers. Therefore, for the energy distribution lines, they want to have quantum networks. This is really interesting. I think this was underlooked in that report. Why energy infrastructures need quantum networks? I can talk about this a little bit because we just finished this business with one of this energy distribution company in Turkey. The Thrace energy distribution company is called TREDAŞ. The European side of Turkey, they're delivering the energy. And they have 3 servers in that region. And each server is looking at least 1,300 transformers. And the data that they send is switch on and off data. Very trivial. You don't want to put some QKD device on a transformer because then you need to put 1,500 of them all together. And all you send is switch on and off data. Just the timestamp of that. That's too much money or too much effort just for that trivial data. But between the servers, you need to use quantum key distribution. And let me also talk about this a little bit. Why did they need to work with us, collaborate with us? They mentioned that, they are constantly under the hackers' attack. And what hackers do is they just access the data in the servers, their servers, because when they switch on and off, in between, they are just looking at the time, and that's how they prepare the bill. They do not know exactly how much energy they provided. They are only looking at the timestamps between switch on and off. And those informations are really critical because you do some future projections to anticipate when you need to switch on, where, and how much energy you should provide, blah, blah, all these things. Therefore, this information at the servers are extremely critical. And they are saying that, they're constantly getting the attacks. Once the hackers have the data at the servers, they look for money. I forgot the term for that. They ask for money so that they can release the data at the servers. And if they don't, and if the other side is not bluffing, so if the infrastructure goes down for 6 months or something, one region in Turkey does not get electricity, Turkey goes bankrupt. So it's that significant. So that they cannot risk, they pay the money, however it is, $5 million, $10 million. And then interestingly, this energy distribution company has some trust relationship with the hackers. They have the trusted hackers and unknown, untrusted hackers. So even if you're a hacker, you have to be a trusted one. So basically, you have to be keeping your words. You have to be a man of your word. So then you say like, I get the money, so now here's your data, unchanged and undamaged, so that you can ask later on again. So that's weird relationship they have between them, and mostly it's Russian hackers, they were mentioning that. And they know who are the hackers and all these things. They kind of leave their signatures so that the energy distribution company knows which group of hackers, so that they know that they are reliable. If they give the money, they will release the data without giving any harm. Anyways, considering all this money they give for hackers, I think the cybersecurity concerns like quantum is something very trivial, like a couple of $1 million for quantum infrastructure is nothing for them. Therefore, quantum is expensive, but there are more expensive things, not getting proper precautions. So anyways, because of that, I think you see that, the Department of Energy is giving lots of money on this infrastructures. And there are some other projects as well. And overall, 2024 was foreseeing a budget of around $1 billion for quantum networks. So you see how the story has changed. US was saying that there's no way we are using quantum key distribution for anything. And then everyone says, oh, okay, then the quantum key distribution goes to trash. We are not using it anymore. No, they're actually investing way more on the quantum networks. Because if you have entanglement, an entanglement-based network, it's only one of the things you can possibly do with the entanglement is quantum key distribution. There are n minus one other things you can possibly do. And therefore, people should build quantum networks. But at the same time, it is a trade-off, how much you want to invest, because things are changing as well. Let's continue with the post-quantum cryptography. I'm not an expert on this field. I don't know much of coding, so that's why I will just summarize very briefly. NIST published 4 types of protocols based on different methods. And they basically want to provide a suite of cryptographic protocols where you can use it for authentication, digital signatures, or loaded data transfer, etc. And I would like to mention one thing that, NIST did some competition and chosen some algorithms and published them. And later on, it turned out that they were totally unsecure. So it is also a trial and error thing. I would like to mention that. But at the same time, there are lots of advantages of PQC. So first of all, it's software-based. It does not require sophisticated hardware like quantum key distribution. Cost-effective because, again, you don't need much of infrastructure. You can build it upon the same infrastructure you already have, communication infrastructure, and you just need some software tests. Built-in authentication. Okay, quantum key distribution is not a key distribution algorithm. I would call it more accurately a key growing algorithm. The first key, which means authentication, should be there. Otherwise, you cannot continue with the QKD. So the first authentication should be done some other way, which is a weakness, by the way. And in PQC, it does not require such a thing. You can do the authentication with the protocol itself. Unlimited reach, no distance limitations. On the other hand, QKD, quantum key distribution, you're sending photons in the fibers, 100 kilometers is the practical limit. If you use free space, because of the shape of the Earth, you need line of sight. Even if you go high altitudes, still at some point, at certain distance, you will lose. You cannot make 1 kilometer towers, right? So there's a limit for that, like 20 meters, 50 meters, something like that, maybe 100 meters, but not more than that. Therefore, again, that puts a limit of 100 kilometers distance. So practical quantum key distribution limit right now is 100 kilometers, terrestrial limit. If you go to satellite, different story. But then again, sending some satellites, launching satellites is an expensive task. Therefore, there are some limitations. On the other hand, PQC does not require anything like that. In fact, you can even use it via cloud. There's a company actually having this business model. I liked it a lot because they do not use some digital device for post-quantum cryptography. They use cloud-based systems. They have some servers. You can use it on the cloud. So therefore, limitations are just removing. So therefore, that's another advantage. And it's possible to operate on cloud-based systems and standardize and valid because these PQC protocols are being built in a way that they are compatible with the existing infrastructures. Remember, we've talked about the interoperability. So this is part of that as well. So we have all these advantages, but there are also risks attached to PQC. Let's just talk about them. First, algorithmic risks, latent mathematical flows. So the psych example, the one that NIST announced that this is the PQC protocol we'll be using. And then soon after, there was a paper that, it's totally unsecure. So that's a good example that there might be some mathematical flows. You think that the algorithms or the mathematical protocol is secure, it might not be because it has to be studied for decades. But right now, we don't have much time for PQC, right? So NIST announced something, people start using it because there's not much time, and then people should start building their infrastructure. Therefore, because of that, there's not much time to test. Performance overhead on constraint device, that's not that much, especially for IAT. Yes, maybe there is, but normally it's not that much of a problem, but still it's putting some overhead. It's good to keep in mind. Implementation risks, physical side channel leaks. We still don't know, depending on the mathematical problems we choose for PQC algorithms, there might be some side channel attacks. They have to be studied as well. And side channel attacks are not that heavily studied for PQC either. So that's a weakness. And the protocol downgrade attacks to weaker crypto and ecosystem risks, lack of crypto agility and switch algorithms if broken. So basically, so now PQC is the way all around the world for quantum computer assisted attacks. At least predominantly, that's considered as the solution. So what if this protocol again breaks, just like the site case, just like this case? Again, we go and build something else. And how much money is wasted? How much effort is wasted? How much infrastructure is wasted? So that's why at some point we might stop doing that and then look for other alternatives. That is a significant weakness. Because the mechanism is not perfectly understood unless you're a good mathematician. I read about this a lot, but I still don't have a clear understanding. On the other hand, as a physicist, I know that quantum physics leads to quantum key distribution. There's an understandable, probably secure system. Global shortage of PQC expertise. That is also true. There are some, cryptography people, mathematicians, they study algorithms, but now they don't know about the Shor's algorithm, how the quantum computer works. But on the other hand, if you work with QKD people also understands about the quantum computer, at least that's up to a certain extent. There is a mismatch. You talk to any cryptography person about the quantum computer, how it works, it's a new thing. They don't understand. But if you talk to some quantum key distribution guy, they understand how the quantum computers work, how the quantum Fourier transform works, Shor's algorithm, etc. So therefore, there's a mismatch on that side as well. And insecure or unvalidated third-party libraries, again, you need to rely on the repository. In this case, I think NIST. So therefore, there are risks associated with the PQC. I didn't mention, I think, the biggest threat. That is, now we think that if you use some new algorithms for PQC, it is safe against the quantum computer-assisted attacks because we are safe against the Shor's algorithm. But remember, Peter Shor published a paper in 1994 or 5, something like that. Right now, if someone in Pakistan or in Turkey find a new algorithm that can break the learning with errors methods or the lattice-based methods in PQC, I don't think that's going to be a paper. That's not becoming a paper anymore. So basically, we don't know what algorithms are out there because, again, certain sections of the quantum studies are confidential. It's always good to keep in mind that we don't know what possible threats are awaiting us for quantum computers assisted attacks. So we are assuming that the Shor's algorithm is the only one. Yes, if that is the case, we are secure with the PQC algorithms, but what if not? Would you like to build the whole country's cybersecurity infrastructure based on that thought? Well, there's a trade-off. We need to think about that as well. So that's another weakness. Basically, there are lots of risks associated with the PQC as well, although it is easier to implement and it's ready to fire. So let's have a look at the comparison of the QKD and PQC. In terms of the implementation and cost, it's obvious that, PQC is the winner, right? So you don't need much money. If you look at the PQC projects, you will see that it's less than $1 million. If you look at QKD projects, in Horizon Europe projects, you will see that they are 3 to 5 million euros. So order of magnitude difference. And infrastructure, PQC works over the existing internet, so existing communication infrastructure and everything. But QKD requires dedicated fiber optic channels, dark fibers, and it has to be end to end. From here to Lahore, if you have a communication channel, fiber, so usually it has relays, right? Repeaters. You don't have quantum repeaters, therefore, the fiber has to be end to end. And remember, you're only limited to 100-kilometer practical distance. So that puts a lot of limitations. Again, the winner is PQC. Authentication, remember, PQC includes the digital signatures and authentication, built-in authentication protocols. But QKD is a key growing algorithm, not a key distribution algorithm. Initially, Alice and Bob first need to authenticate themselves. And you need another protocol for that. And it's not certain what is going to be used at this stage. So therefore, there is another weakness. Again, the winner is PQC. Distance, well, we just mentioned it. There's no distance limitation for PQC. And there's NATO's Diana program. So there was this 2025 cohort demonstrations. And one of the companies, I think it was in Quantropy, at intercontinental PQC from cloud-based systems. So there's no limitation. You can use it in any way. But on the QKD part, there's 100-kilometer terrestrial limitation. If you go to space, there's no limitation. But then an optical ground station is not an end user. Still, from the optical ground station, you need to have fiber-based network. Again, there are lots of limitations. The winner is PQC again. Security basis, I think now we come to our part, right? Most of the people here are either engineers or physicists. So the security of QKD is relied on the quantum physics, either the bit error rate or violation of Bell's inequality. Either case, the security comes from the quantum physics, either no cloning theorem or violation of Bell's inequality. On the other hand, for PQC systems, it's based on the mathematical difficulty. It's not even a solid argument. It's just difficult. It's not, certain. So in that case, the winner is definitely QKD. It's much more secure. That is why I think they made this analysis here. You see, if you look at the Saga and Eagle one, on the Saga part, they only use QKD. Only QKD, because that's more secure. If the governments want to talk to each other for strategic tasks, they want to use QKD, not PQC. So I think they come to the same conclusion with us on this slide, that, QKD is definitely more secure. But again, it doesn't mean that it's 100% secure. You still need to study the side channel attacks. And I think the capability basis, I think this is one of the most significant one, because with entanglement-based networks, there are lots of other things you can possibly do. And tomorrow I will be giving a talk on one of the possible applications, the quantum position, navigation, and timing systems. And eventually it turns out to be a quantum GPS system, something you can never do with the PQC. So there are these kind of advantages coming in if you have a quantum network. But you have to use entanglement. So let's talk about this cautiously optimistic approach. And I just put it into two segments. Short-term strategy. By the way, I would like to mention that, I'm just writing a national security plan on, what was this? Presidency of defense industries of Turkey. We are preparing a roadmap for Turkey, and I'm writing the roadmap for quantum communication side. Some of them are the conclusions that we come up with that study. And there are 354 organizations and companies attending that event. It's a really, really large one. And we are writing the report collaboratively. And some of them are the conclusions of those reports. And also we are collaborating with NATO in that sense. So basically these conclusions have lots of studies, papers, literature reviews, and discussions behind it. PQC first. So we need to start with PQC. In the near term, people should familiarize themselves with the PQC algorithms. There's not much effort needed, not much money needed. We just need to find the right people, software people, and mathematicians come together and understand a little bit of, not much, a little bit of quantum computer assisted attacks, and I think we can explain them. So then we just make a nice consortium, and then we study PQC algorithms. And I think more than 99% of the companies will receive, and organizations will receive the cybersecurity they need at this stage. So this is a very fast action we can basically take. And that can be a nationwide action. So it just requires some decisions. And basically that gives an immediate quantum readiness up to a certain extent. And QKD pilot projects. So basically deploy small scale, high impact QKD zones. Not big, maybe in the metropolitan areas. Singapore is doing it pretty nice actually. They just had a 20-kilometer small network, 20-kilometer distance, diameter network. They're just testing different things. Some academicians build some quantum memory. Oh, okay, bring it, and then let's test it with our entanglement-based network. This kind of approach. I think this kind of studies is also helping on this side, human capital. We'll come to that stage. But I think a big mistake, especially for not so developed countries, let's say, is a national network. That is something, I know it sounds really nice. Everybody's going to be proud. Oh, Turkey has, or Pakistan has this national, nationwide network, quantum network. This might not be the best idea at this stage because there are lots of things to be tested. Let other people test first, and then we become ready. Okay. If you're not a good swimmer, you don't want to jump in the water, right? Let's see someone swims first. Then you slowly put your feet while your one foot is on the land, right? That's the approach. I think that is healthy approach in a way that, you do not miss the technology, you are ready. You also have precautions because you have the PQC infrastructure, but at the same time, you're building your human capital because that is the biggest element to be the winner of this race, let's say. I don't think whoever puts the most money is going to be the winner. Whoever has the most talents is going to be the winner because we don't know where the technology is going to converge, not yet. So therefore, being ready at the same time, not putting all the efforts because we don't know where it's going to lead, but at the same time, being ready for this kind of technologies, cyber threats, because we know that the world is getting heated up. Lots of technologies are becoming really, really important. And I think people should be ready for, there should be some quantum readiness in that sense. And human capital is, I think, the most important element here. And the way to do that is not miss the second item, the pilot projects. There should be lots of pilot projects. People should be working on them. And it's not to look down because that efforts are really, really significant. When you want to have a nationwide quantum network or build quantum repeaters or something, you have the people to do that because eventually it all comes down to human capital. And long-term strategy requires network scaling, gradually build a national QKD backbone using trusted node. There's a really large one. This is the Chinese network. This 4,600 kilometers. It's huge. It's huge, literally huge. And all the fibers are end to end. If you see there are two nodes, like any of these two nodes are end to end. For example, if one of them is 100 kilometers, there is no gap or anything. There's no measurement because if you measure the quantum state, it collapses. You have to let the quantum state until the other end. And imagine 4,600 kilometers network. And I know there are lots of attacks, and some of the attacks I didn't publish because of other reasons. So if there's any need, we can use it. So you understand the point. So basically, not all the side channel attacks, not all the problems, not all the loopholes are pretty understood, right? Therefore, building such a network might not be the best way, especially for developing and how do I say? Well, I guess we can generalize it. I think it doesn't make sense to put all the eggs in the one basket and spend so much efforts on this one. And that's a good example of what not to do in this case. That's one of my, again, subjective opinions. Sovereign industry, that's really, really important. And we know from the pandemic times that, if you cannot get the product, doesn't matter how trivial it is, right? Semiconductor industry is cheap labor, right? That's all you need. Wherever there is cheap labor, you put the factory there. But then if you don't have it, you don't have it. If you don't have the chip, you cannot make automobiles. So therefore, especially for quantum studies, you need to be able to access to those modules, those technical devices. And you cannot expect all the quantum physicists to build the detectors, lasers, and everything, right? You have to buy certain things so that you can do research. Therefore, how the thermal light is bunched? I think there's a bunching happening for quantum clusters as well. So if you want to access, for example, a quantum Josephson parametric amplifier-based quantum chips, they're not selling anywhere. And, so you just send an email to Quantware, they will just check where you're sending the email from. So therefore, it's important to build your own infrastructure. You need to have your fabs and production capabilities. That's really significant. And future R&D, the next generation technologies should start in the long term, not to rush, but like technologies like quantum memory, then quantum repeaters, and satellite-based networks, etc. Yeah, thank you.
Assalamualaikum. Nice talk. Okay, do you think without QKD we can save our infrastructure with post-quantum cryptography?
Sorry, the question is, without QKD, can we
save our infrastructure or communication with post-quantum cryptography? And can quantum random number generator replace this QKD? We are generating key through QKD.
Can we secure the infrastructures without QKD and with PQC? That's the question, right?
Yes.
Okay.
And second is that you have mentioned that QKD protocol implemented that E91. Is there any product in the globe that they have implemented?
Yes, yes there are. The second answer is very easy. Yes, there are lots of products available. But you know, if you look for some standards, yeah, maybe they're not suitable to standards. But what are the standards anyway? They're just definition of what is QKD. There are not many standards. If you just skip the standardization part, there are lots of products available in the market for QKD-based protocols. And regarding the first one, the answer is saying that PQC is the way to go is wrong. No one knows that. We are all speculating. Of course, there are some sign tables. We're just looking at them and then looking at the map where we are, trying to understand what should be the way. But these are all speculations. No one knows what's going to happen. In that case, it's not an either/or question. But we don't have to. We don't get to choose. It's too much luxury to choose it. And just look at US. They say we will never use QKD for official things, but then they are boosting the budget for quantum networks. So you cannot just choose one of them. So basically, it has to be a side-to-side study. And I think, so this part is very important. So it's really relatively easy. It just depends on one decision for a nation to be ready for PQC implementations. So once that decision is taken, then the next step is having the pilot projects, not nationwide, like, you know, $900 million for, no, small projects, research projects, so that there are people who knows how to handle those modules and who knows what are the challenges, problems, and they can act when there's a need. So I think that should be the healthy way to go. So it's basically, it's a hybrid approach. People should study both. Yeah.
One more question, but very quick, please.
Thanks for the wonderful talk. So I want to ask that you talked about trend shift from QKD to PQC. So what should be the stance of the students that are studying QKD and doing research in QKD? Should they move on to something else, or should continue to do research in QKD?
Okay, what should be the
stance of the students that are doing research in QKD?
I understand that you're more familiar with QKD, but not same for me. I'm the same. So I don't think, you know, we can just start learning about this mathematical, you know, algorithms, how they work and all these things. And the cybersecurity is like a, you know, endless topic by itself. We need to familiarize ourselves, but we cannot just dive in. I think we need to be able to talk with cybersecurity people. There is a term for this, quantum readiness. So they should be quantum ready. We should be PQC ready. Not more than that. We cannot just start becoming, I think AI is a good example. Some of physicists are dropping all the physics and becoming AI people. That doesn't work. So that doesn't work. That's not a good approach. But understanding and, you know, getting the benefits of each side is the way to go. That's what I would do. And if I was a PhD student, I will also do that.
Sir, please, we can talk on deep. If you can discuss the matter on these. Kadir Saab is here. Now we will gather again after the tea at 11 o'clock. There are two announcements for the students. First, the students are requested to submit their poster at the INSC office near reception. The second is also about the students. You have to prepare a single slide presentation for the poster. That is just for 5 minutes. So please prepare your presentation. Okay, thank you very much. We will again gather in this hall at 11 o'clock sharp.